Good day, dear colleagues and conference participants. I would like to thank you for the opportunity to be today with you in order to present our research work on the topic of investigation of enhanced mathematical model for traffic engineering fault-tolerant routing. It is a collaboration work between Alexander Lemeshka, Alexandra Yeremenko, and me, Amal Mersni. Let me introduce briefly myself to you. I am Associate Professor at V.V. Popovsky Department of Info Communication Engineering at Kharkiv National University of Radio Electronics, Kharkiv, Ukraine. Fault-tolerant routing is critical for modern communication networks to achieve high availability and reliability through routing mechanisms. There are several technological solutions to adopt in order to increase the fault tolerance aspect in the network. Among these solutions, we can mention IP fault-tolerant routing that includes several protocols known as the first hop redundancy protocol FHRP. It is highly recommended to develop analytical methods and solutions of fault-tolerant routing under gateway redundancy techniques. Thus, the mathematical model of traffic engineering fault-tolerant routing has been investigated in this study with the goal of supporting the default gateway redundancy strategies and network load balancing by analogy with the first hop redundancy protocol FHRP mechanisms. In the following slide, an overview of first-hop redundancy protocols is presented. FHRP, as mentioned in the previous slide, refers to a collection of protocols. In fact, one of the redundancy technologies is to implement the redundant gateway. The primary problem in terms of gateway redundancy is that the router device itself. When the router or communication link breaks down, then the access to the external network is totally lost. As a result, a second redundant router must be deployed to avoid the disconnection of the gateway network. This is often where the FHRP protocols inherent play to address the difficulty of end devices configuring multiple gateways by enabling hosts to automatically transfer data to the redundant router without requiring manual configuration modifications. The FHRP group contains several protocols. The widely used among them are the following: Hot Standby Router Protocol, HSRP, Virtual Router Redundancy Protocol, VRRP, and Gateway Load Balancing Protocol, GLBP. The Gateway Load Balancing Protocol, GLBP, is another Cisco proprietary redundancy protocol. It enables load sharing of packets across a set of redundant routers. GLBP guarantees load balancing capabilities for multiple gateway routers with the same IP address but with distant MAC addresses. In GLBP, all routers operate as active routers to prevent the whole system from collapsing. In the GLBP group, the roles are also defined by devices' priorities, with the rule of the highest priority gaining precedence. There are two leading roles of gateways: one active virtual gateway, AVG, and up to 4 active virtual forwarders, AVF, per group. AVG replies to ARP requests for the default gateway's MAC address. IVR in the charge of traffic routing. This improves the network performance by providing load balancing and IP redundancy. The next slides explain the proposed enhanced mathematical model of traffic engineering for tolerant routing. Let us consider the structure of telecommunication network described by the graph G and represented by the following figure. It is composed of a set of vertices M, which includes two disjoint subsets R and V, where R displays a subset of the vertices that correspond to the routers in the core network, while V indicates a subset of vertices that corresponds to the access networks. The set R also consisted of two disjoint subsets. The first set represents the edge routers, while the second set represents the transit routers in the core network. Secondly, the set of edges also contains two subsets. The subset E corresponds to the core network links, while the subset W corresponds to the access network links. For every arc E, its weight capacity is introduced. It characterizes the bandwidth of the communication link simulated by this arc. Let K be the set of flows incoming to the edge router from the access networks. For each kth flow correspond the following parameters. The first parameter is the access network, which is the source of the kth flow, while the second parameter represents the destination access network for the kth flow. Moreover, the third variable, lambda k, is the average packet rate, also referred to the intensity of the kth flow at the address of the network. It is measured in packets per second. The three following control variables represented are in charge of implementing the fault-tolerant routing. The first variable is the routing variable that represents the portion of the kth flow that passes through the communication link. The second variable, it is the access variable that represents the portion of the kth flow in the access line, while the last variable is the access variable that represents the portion of the kth flow in the access line. The multipath routing conditionals are implemented in constraints 1 and 2. In order to prevent the packet loss, the following conditionals 3 and 4 are represented. The routing variable must conform to the coming flow conservation conditionals represented in the expression number 5 to ensure consistency throughout the calculations. Following that, other control variables defining alternative backup paths must be included to enhance the routing fault tolerance when access networks are linked to the core through a particular virtual router interface. Similar to the primary case, the alternative routing variables are constrained by expressions from 1 to 5. The satisfaction of protection conditionals 6 to 8 protects the border router. According to the requirement 6 to 8, the alternative route can not use all outbound links from the protecting node. To guarantee load distribution throughout the routing process in the network under the concepts of traffic engineering in the proposed model, the criteria of overload prevention are introduced for both primary routes and backup routes, and they are represented respectively by expressions 9 and 10. Upper bound of the network links utilization is represented in expression 11. Optimality criterion is represented in expression 12. In this work, we study the processes of fault-tolerant routing. Figure 1 displays the network structure for numerical research. Gaps of communication links indicate their bandwidth measured in packets per second. Let's suppose two packet flows with intensities, the values of which varied from 10 to 700 packets per second, which are transmitted from the access network V1 to V2 during the study. The bounded alpha were estimated when implementing the default gateway protection scheme in the event of a border router R4 failure. By analogy with the well-known SHRP protocols such as GLBP, the load balancing across virtual router interfaces is possible, and it is represented in the expression number 13. Figure 2 and Figure 3 are represented in the following slide. Figure 2 shows the dependence alpha on the intensity when using the primary routes for a balancing option similar to the GLBP protocol. Condition 13 ensures load balancing not by packets but by hosts, means that flow packets originating from a specific host can be routed to a single border router in general Hosts can use different border routers whose interfaces form the default gateway virtual gateway. Figure 3 shows the dependence on the intensity values when using the primary routes for the balancing option under the proposed model expressions from 1 to 12. Figure 4 shows the gain in terms of alpha obtained from using the proposed model expression 1 to 12 in comparison with GLVP solutions expression 13 using the primary routes. Thus, the application of the proposed traffic engineering fault-tolerant routing mathematical model when using the primary routes makes it possible to reduce the upper bound of the network links utilization alpha from 10% to 25% in the region of low intensities arriving at the network and up to 40% otherwise. Figure 5 shows the dependence on the intensity when using the backup routers for a balancing option similar to the GLVP protocol expression number 13. Figure 6 shows the dependence on the intensity when using the backup routers for a balancing option according to the proposed model expression 1 to 12, while Figure 7 shows the gain in percents in terms of the boundary value obtained from using the proposed model in comparison with solutions similar to GLVP protocol expression 13 in the case of using backup routes. Therefore, applying the proposed traffic engineering fault-tolerant routing mathematical model with backup routers allows reducing the upper bound of the network links utilization up to 30% in the region of low intensity arriving at the network and up to 60% otherwise. The investigation of an enhanced mathematical model for traffic engineering fault-tolerant routing was carried out. The model is flow-based and represented by mathematical expressions from 1 to 13. The choice of the optimality criterion organizes load balancing in the core network and access level. The model covers the implementation cases of default gateway protection schemes. The application for a specific network topology, represented in Figure 1, shows improvement of the routing solution's fault tolerance and reduces the upper bound of the network links utilization. Reducing the upper bound of the network links utilization contributes to improving the network performance, average end-to-end packet delay jitter, and packet loss probability, which are the leading QoS indicators. The directions for future research are related to the extension of the parameters to be protected within the fault-tolerant routing processes to the quality of service and network security indicators. I would like to thank you for your attention.